Okay, so we are going to go over an introduction to calculus. So we're going to look at the idea of kind of what calculus is and where it kind of comes from and how it applies to maybe things that we have done already and then things that we're going to move on to. So first of all, to start us off, we're looking at what is the slope of the following two lines. So we're going to start with the line on the right hand side, and the usual way that we might remember from doing these slopes from before would be that we calculate what we call rise over run. And what this means is by the rise we're talking about the y values. So how do the y values go up is usually what we mean by rise, but it could be go down. Sometimes we say that's a fall, or we might just choose to write the rise as maybe a negative number. And run then refers to the x values, so as the x values go across. So the way that we usually do this in calculating our slope with our rise over run is we pick a point. So say we pick this point here, 2 or 0, 2. We go across a certain amount, so say we just go across one space. So that means our run is going to be 1. Then we want to see how far up do I have to go to still be on the line. So going from that point, how far, if I go over 1, how far up do I have to go to still be on my line? So we draw our dotted line up, and we can see from the y-axis there that one of these squares actually has a value of 2. So my rise is going to be 2. So if we write it along the side here, my rise over run for this line is equal to 2 over 1, or just 2, whichever we prefer. We can do the same kind of thing for the next line, the line on the left hand side there. So say we pick a point again, we can pick maybe 0, 6 here. And we're going to see if we go across first. So looking at my points on my line, we can see if I go across one step, it might be difficult to work out that y value accurately. So maybe we'll try going across 2 steps. And it's good for us to see here that it doesn't matter how many of the steps we go across. So my run here is going to be 2, and I'm going to have to go down all the way from 6 down to 0, which means I'm having, I suppose, a fall of 6 if you like, or a rise of -6. So here my rise over run is going to be -6 over 2, which is -3. And what this tells us about this line is how steep the line is in the first place, so that the one on the right hand side there has a slope of 2, the one on the left hand side has a slope of -3, but it also gives us an indication of how the y values change as the x values change. And if we look at the next part, so that's just kind of what I have written here, with rise over run we're looking at how the y values change as the x values change, and instead of slope we can say rate of change. This is kind of the new phrase that we bring in with this chapter, rate of change. So when we talk about the slope, we're saying the rate of change of y as x changes. So saying there for line B, our slope was 2, that's what we calculated up above. We got our rise over run was equal to 2 over 1, or just 2. And we can say the rate of change of this line is 2. And what this means is that as x increases by 1, y increases by 2 units. So rate of change and slope, we can kind of think of them as kind of interchangeable for this instance. Slope is is considered to be a rate of change. So in calculus, the way that we would write this rate of change is this notation dy dx. And obviously that's equal to 2 at the moment because we're still talking about the same line. And this dy dx has a particular meaning. And we can think about it as the rate of change, yes, rate of change. But the rate of change of what? It's the rate of change of y with respect to x. And what we might need to remember here is that when we draw our lines, those y values are usually dependent on the x values. We usually use those to find the y values. We use the x values in order to calculate our y values. So when we're saying rate of change of y with respect to x, it's kind of coming back to that idea that the y values depend on the x values. So dy dx is the rate of change of y with respect to x. And we might have some other letters in there depending on the questions that we're looking at, so long as we remember that the one on top is the one that we consider to be changing with respect to the one on the bottom. Okay, that's generally the way that we go with it. So if we look at an example, the example says what is dy dx of, and then we have 4 different equations here with y's and x. So hopefully looking at these equations we should think that they seem somewhat familiar to us. And if we kind of cast our mind back, I suppose, a little bit, maybe to last year when we would have done coordinate geometry of the line, this is the equation of a line. This is usually how we would write a line, and you would have seen this at junior cycle as well. So this is what we call the general equation of a line, and in this general equation, this letter here, this letter m, is what we would call the slope. So the letter in front of, the number in front of the x, the coefficient of x, is generally the slope of the line. So when we're being asked to find dy dx here, we remember that that's the rate of change of y with respect to x, but in our own terms, for a line, that's going to be the slope. So for our first question here, part I, the slope of the line is going to be 2. Okay, so we can even just maybe to make it even more explicit, let's write out dy dx is equal to 2. For the second one, dy dx, same thing again, the coefficient of the x is equal to -4. For the third one, we're following the same thing again, dy dx is equal to 3. And finally, dy dx is equal to 7 for this last question here. So when we're looking at a line, finding the slope or finding dy dx actually ends up being fairly easy because we're used to working with lines and we're used to finding the slope. And this rate of change and dy dx and all of this new notation, because with the line we're just thinking of that as being our slope, we can kind of calculate it fairly easily and fairly comfortably. When we move to other functions is where we see some issues. So looking at our quadratics, for example, we know that a line has a constant slope, that the slope is the same no matter where on the line we start or where we look at. And we saw that with our rise over run, that if we picked a point and we went over a certain amount, we wanted to see how far did we have to go up to still be on the line. But no matter what point we picked to start at, we would get the same slope. And that comes back to the equation of the line, because we can see the slope within the equation. If we look at a quadratic, the slope of the quadratic is constantly changing. If we scroll down a little bit even just to look at this diagram, we can see that along this first kind of half of the quadratic, so if we see kind of maybe this yellow part here, the quadratic's going down the way, it's decreasing. And generally if something's decreasing we would say that the slope is negative. But over on this side, the slope is increasing. So obviously we can see straight away that the slope on one side is different to the slope on the other side. There might also be a case that the slope is at different levels of steepness at different points on the graph. So it's not as clean cut as we've had with a line. So what we've written here, I suppose, if we kind of talk through this, is that in order to estimate the slope at a particular point, we call a tangent to the curve. That's this phrase here, so tangent to the curve. And a tangent is a line that touches the curve at just one point. So we have an example of one here, touching the line at 2, 4, and then it goes way off. It doesn't touch the line at any more points. So if we think of, if we go on a tangent, we generally start from where the conversation is at, and then we go way off in a different direction. So a tangent to a curve will touch the curve at one point, but one point only. But to calculate the slope at this point, we draw our tangent and we get the slope of that tangent. So we can see here on the right hand side, calculating the slope with rise over run, the slope at that point is equal to 4. 4 over 1, or 4. And that's the slope at this particular point, 2, 4. But if we were to pick a different point, we could end up with a different slope altogether. And even looking at this here, we can see that this is really, really time consuming. We wouldn't want to be tasked with having a load of questions to do where we have to calculate the slope of this curve at a load of different points, and we have to calculate that by drawing a tangent at each of those points. That's going to take up too much of our time. So what calculus lets us do is work out these slopes using different rules, using new rules for us. And these rules will let us work out kind of a general term for the slope of the curve. And with that general term, we can work out the slope at a particular point. That's what we're going to look at, I suppose, in the next sections. So this section is just supposed to kind of introduce us to what the idea of calculus is and how it relates to slopes and things like that.